Hello, welcome back. Today we will talk about bonding. Bonding is so important for chemistry because otherwise life would be a very boring place if all the atoms would be happy like the noble gas atoms. So therefore, because of the atoms wanting to achieve a special stability by getting what we call a noble gas electron configuration, they will somehow shuffle their electrons around to get certain magical numbers, so to speak, and this leads to a bonding between the atoms, which can develop into all kinds of structures, which makes our life so diverse and exciting. So let's see what we'll discuss today. The driving forces for bonding that I already touched upon right now, the valuable Lewis dot structures that allow us to follow through the procedure of chemical bonding. The driving force being mainly the octet, therefore we call it the octet rule, that the valence shell achieves an octet, an electron octet, although there are exceptions to that rule, meaning complete electron shells essentially, particularly the valence shell. The mechanisms of achieving this goal, the electron transfer mechanism, which leads to ionic bonding because ions are formed as a result, and electron sharing, which is another way, a strategy to obtain the noble gas electron configuration or complete shells. And then how can we know what atoms will do? What procedure will they choose for their octet, for achieving this special electron structure? And it depends mainly on the electronegativity value that the atom has or the element has. Remember, electronegativity is the electron affinity, which can be measured, plus the ionization potential or ionization energy divided by 2. There are a few different modifications of this type of calculation. We usually use the so-called Pauling, Linus Pauling values, but don't take everything too literally because depending on what type of table you get out of certain literatures, it can vary by 0.1 or 2 or something like that. So don't take it too seriously as far as the values go. So the electronegativity difference we want to determine as delta, meaning difference, En, electronegativity for short, and the resulting polarities of covalent bonds when we have them. We will look now at our first overhead here, and we will take the example of sodium and chlorine and the possibility of another chlorine atom bonding to the first one. So the chlorine wants to have an octet, as we can understand. The Lewis dot structure of the atoms here shows the valence electrons as dots. Now there's no special way of grouping them around the atom, the atomic symbol, but we usually pair them off as couples or pairs. We call those then lone pairs. And we see also some that are not paired off. So that means chlorine, for instance, has 7 electrons, so it has 1 unpaired electron. So this electron wants to find a partner because if another electron could be incorporated into that valence shell, then guess what? Chlorine will be a quasi-noble gas as far as the electron configuration goes. It will have achieved an octet and will be close to argon, which is the next noble gas in that particular period down the road, so to speak. We have here sodium with only 1 electron, so it's an alkaline metal. It has only 1 electron in its valence shell, so it wants to get rid of that electron because once that electron is gone, then the lower shell will surface and become the quasi or the so-called valence shell, the outermost shell, and that will be, of course, a complete one. So sodium has a very low electron affinity. That means it wants to get rid of that electron. Chlorine, on the other hand, has a very high electron affinity. It is greedy for another electron. So they both have a certain goal in mind, and therefore they will do what we call an electron transfer. Sodium will transfer its electron onto the chlorine, and as a result, we have automatically ions that form. Because remember, sodium will not be electroneutral anymore. It will have one extra proton in the nucleus in number than the amount of total electrons in the shell. So therefore, it has a residual charge of +1. So therefore, it becomes an ion that has the charge of +1. Chlorine, on the other hand, now also has a disbalance between electrons and protons. It has an extra electron. Therefore, the residual charge is -1. If we compare the number of positive charged species, which are the protons in the nucleus, and the number of negatively charged species, which are the electrons in the shell. So we have a disbalance, meaning that the chlorine now is very happy with its octet, but the price to pay is that you become a charged species. That means your behavior changes. You have an electrostatic force field all around you, going in all directions. So that means you attract any type of oppositely charged ion. Remember, opposite charges attract, like charges repel. The same thing goes for sodium. Sodium has a positive electrostatic force field and will attract anything negative in its vicinity. Therefore, the result is that we get a conglomeration of ions that organize themselves into a specific pattern depending on their ionic radii, the power of their electrostatic attraction or whatever. So that means we have a special type of crystal lattice structure, which can be cubic, like with sodium chloride. It can be rhombic, orthorhombic. There's 7 basic crystal lattice types. We would call this type of crystal an ionic crystal because the building blocks happen to be ions. And you see the closest packing of the ions. This is regulated by a lot of forces, but the main thing is the amount of charge and the size of the ion. I have here a model which is not sodium chloride, but a similar type of lattice, which is calcium chloride. So calcium is 2+ and chloride ions are -1. So the formula of a formula unit would be calcium or CaCl2 instead of NaCl. So the charges are different, therefore the formula will be different. We call a repeated segment of the crystal a formula unit, which can be represented by the formula as we know it. Like NaCl is a repeated quasi-element, not a real element of course, but a segment that repeats itself throughout the crystal. So we do not have molecules here. Due to the electrostatic force field, which is very symmetric, point symmetric around the ion, this will of course lead to an attraction from all directions. That means the crystal builds up very quickly. So that is the result of an ionic bond. So it's a non-directed attraction, and we do not have separate entities like in the molecular type, which is the other type of bonding that I want to discuss with you here today. So I'm going to go back and show you that these 2 chlorine atoms can get the octet in a different way because each chlorine doesn't want to give up an electron. They want to receive one, but they come into a kind of consensus and tell each other, look, let's put 2 of our electrons together, make an electron pair, and we both can use it. We both can utilize it. That is what makes them then conjoined twins, you might say. So they make a molecule. So they have to stick together now until something does part them. But otherwise, they can stay like that for the rest of their days. So what we do is one electron is donated and the other electron is donated for the mutual electron pair that they share between them. We can then distinguish between what we call the bonded electron pair and the so-called lone electron pairs. The lone electron pairs are still attributed to one atom, and the shared electron pair is attributed to both atoms. And this electron pair we can symbolize by the so-called valence bond line, which has to go and connect the two atoms in a horizontal fashion or vertical fashion, but it's never written close to the atom like we do the lone pairs. So it connects the centers of the two atoms. This is a symbol for us chemists. So we can distinguish easily in the so-called Lewis dot structure the lone pairs and the bonded pairs. Now the bonded pair, remember, is used by both partners. So therefore, if you look at this picture here, the left chlorine has an octet and the right chlorine has an octet when both utilize that shared electron pair between them. So this is what we call a directed type of bond. And we get single entities, which we call molecules, that can move around on their own. They're not stuck to a lattice like the ionic bond. However, if we would solidify chlorine gas or molecules, they can still make a crystal, but we don't call that an ionic crystal. We would call that a molecular crystal. So the difference between covalent and ionic is that the covalent bond leads to molecular species. It's a directed bond. And the covalent, that's what covalent means, same valency of the bonding partner. And the ionic bond means heterovalent, actually, although we don't use that word much, meaning different valencies. Now I will quickly show you this in a quick example. I'm going to put here the lone pairs or the electrons onto my symbol so that you sort of have an idea how this works. This is now what I'm doing is a Lewis dot structure for the chlorine atom. And if I take a metal like sodium, I hope you can see it, should look a little metallic, then that has one electron. And what we'll do is one of these electrons will be given to the chlorine. And now the result is, as you have already learned, that we have a negative species and a positive species. And that means they have to now move together. And that means, since the force field is going in all directions, we have another sodium ion coming close, and so on until the whole chloride ion is surrounded by sodium ions, cations in this regard, and then another chlorine will come here, and so on, and so on. A crystal lattice will quickly build up. So that's the result of ionic bonding. But if we have the molecular or covalent bonding, then it's a little different. And I'm going to make you a, see, this is like a little game one can play here. Put the little lone pairs or the electrons around the symbol. So I need a few more. Because chlorine, remember, is in the 7th main group, so therefore it has 7 valence electrons. One more, and then we're ready. And I still have to put another one, and then we're really ready. Okay. Here are the two chlorine atoms. So what they will do, okay, let's use those two together and make a molecule. So now we're stuck. Move them closer together. And this would be the Lewis dot structure for the element, the diatomic element chlorine. So this electron pair is shared by this chlorine, and this electron pair is also shared by the left chlorine. So that's a very stable molecule because they both have the electron configuration that they strived for. Now, I talked already about Lewis a lot. Lewis was a very famous American scientist that revolutionized the idea of making, describing the bond as a shift in electrons. Other people also were involved, like Kossel, a German physicist who had theories about bonding. Linus Pauling, also a very important chemist who wrote a book, The Nature of the Chemical Bond, and who also was the person who perpetrated the vitamin C theory about eternal health. And he died at a very ripe old age, which might prove something, but who knows. Let's move on and discuss the Kossel-Lewis theory. That means the outer electrons are shown as dots in our elementary symbol. And remember, when we transfer electrons, then here's a picture of Lewis, by the way. And if we transfer electrons, then we have ions. And according to the Lewis dot structure consensus or guideline, we have to write ionic structures with brackets to keep the ions apart. So to differentiate between a molecular or covalent bond and an ionic bond, we use brackets or not. So for ionic bonds, always brackets must be used when we want to use the Lewis dot structure terminology. And the charge is sometimes written within the brackets, sometimes around the brackets. We don't worry about that too much. You find both ways of describing this type of structure. So here again we have electron sharing and electron transfer, two possibilities. We cannot use the valence bond line for ionic bonds, and we cannot use the brackets for covalent bonds. So we have to be a little strict here in the types of electron dot structures. Now here I'd like to show you how this looks in the shell environment. Sodium has 3 shells. It has 2 in the first shell, in the so-called K shell, and 1, 2, 3, 4, 5, 6, 7, 8 in the second shell, the L shell, and only 1 little lone electron in the outermost shell. Now remember, the octet rule means that the valence shell cannot have more than 8. It can have 2 for hydrogen and helium, but for all the other atoms, regardless of how many electrons this shell could theoretically have according to the 2n square rule, 8 is the limiting factor as far as the valence shell goes. Chlorine is a little smaller, remember, because of the attraction, Coulomb's law of the positively charged particles and negatively charged particles, so it's a little tighter packed as an atom. But when sodium donates its electron to the chlorine, which is the electron acceptor, then things change. As we see here, the whole structure for sodium shrinks because the total shell is gone with that little electron. And chlorine, incorporating that special gift of sodium, that extra electron, leads to an expansion of the shell because of the electron repulsion. We have 1 electron too many. So therefore, the ionic radius gets larger. But as I've shown here with the little zigzag lines, both of these species now are ions. They have an electrostatic force field, meaning they attract anything oppositely charged in their environment, which is usually the oppositely charged ion that is in its vicinity, and the crystal growth can proceed. If you look carefully at sodium chloride crystals out of your salt shaker, you see little cubic crystal lights. Now, if we look at the electron dot structure or the electron configuration of the sodium ion, it has 2 and 8, or 1s2, 2s2, 2p6, if we use the sub-energy levels, the distribution of the electrons in the orbitals, and it represents neon, electronically speaking. That means sodium didn't become neon, but the electron shell is equivalent to neon, a noble gas. And chlorine, having now still its 3 shells, sodium lost a shell, remember, then it becomes a quasi-argon. Quasi means sort of an argon. But we know that it's just as far as the electron shell where the similarity goes. Here we have now in our slide electronegativity values. And I remember I told you not to take them too much for granted. But usually they're pretty close, depending on what kind of table you use. The by far most highest electronegativity value is found for fluorine, which is 4.0. That means fluorine has an extreme attraction for electrons. And the lowest is francium with 0.8, which is a metal. So you can see here the diagonal trend of increasing electronegativity values. That means it's the tendency of the element to attract electrons within a bond, having already made a bond. So the more electronegative elements will draw the electrons towards themselves. It's just like two people in a bed, and one pulls a blanket over and the other one has naked feet or cold feet. So that means it leads to an unequal sharing of electrons if a covalent bond is formed, and that is the concept of polarity, which will be discussed in more detail in our next bonding episode. But you can roughly say that the larger the electronegativity difference is, the more likely we have ionic bonding, and the closer the electronegativity difference is between the atoms that are ready to bond, the more likely it is to have a sharing situation, meaning a covalent bond. So the nonmetals, the ones that here on the top right-hand corner of the periodic table, will prefer to do the covalent bond, and the metals with nonmetals will prefer to undergo ionic bonding. Now you might say, where is the cutoff point? That is very difficult. I would say a rough guideline is if the electronegativity is greater than 1.5, you can predict more of an ionic bonding situation. If it's less than 1.5, then you can predict more of a covalent or sharing electron pair situation. So that's why the electronegativity's values are quite helpful. Notice that the transition metals are pretty much the same. There's not much variation here. And of course, with the rare earths, they're almost all the same, like 1.1 as you see here. But the big variation is here on the right-hand top corner. Now, I talked to you a little bit about polarity. And that can be also determined by the relative electronegativity. Here, this molecule, the Cl2 molecule, is completely nonpolar. Why? Because both atoms have exactly the same electronegativity value. They're both 3.0. So the difference is 0, meaning the electron density between the two atoms is balanced out, so no shift. However, when I remove chlorine and put a hydrogen here, and maybe I should use a little dark space to show that. Here I have hydrogen, which comes in with 1 electron, and here I have chlorine with as you know already, 7 electrons. Let's scoop them around here a little bit. It's a little tedious to do this, but it certainly is helpful to understand. Let me use my little stick here. It's like playing billiard or pool. Okay, and they will make an electron pair bond, these two, hydrogen and chlorine, because the electronegativity difference is not so much. Chlorine has 3.0 and hydrogen has 2.1 as an electronegativity value. So the difference is 0.9, right? Meaning that chlorine will be more greedy for the electron pair. So the density of the electrons is more situated on the side of the chlorine. This is a molecule, it's a covalent bond, naturally, as we have predicted. But this, the hydrogen is slightly positivated, has the naked feet in other words, and the chlorine is slightly negativated. That means they don't have a full charge, but since the electron density has shifted a bit, chlorine is sort of top heavy in electron density and hydrogen is a bit depleted. This is what we call a polar bond. Now remember, I could substitute an electron pair that is shared with the bond line, right? So we see here the bond line. So this would be then the Lewis dot structure, so to speak, of the hydrogen chloride molecule. But the shift is in direction to the chlorine. So chlorine is what we call a delta plus species, and hydrogen is the delta, chlorine is the delta negative, and hydrogen is the delta plus. So we see here again how the polarity has come about when we have a difference in electronegativity values. We can indicate that by the delta minus and delta plus symbols or the polarity vectors. And it's just like having horses in front of a buggy. And thank you. We'll go on next episode with this chapter. Goodbye.